All right, so let's have a look at the final section or final example from this section. So to wrap up Newton's laws, we're going to be having a look at his second law. So his second law, it's not, I don't know if it's any more important than the other ones, but this one is the one that you're going to be probably the most familiar with. And just from a practical standpoint, this is the one that you're going to be dealing with every single day because it is the one that most explicitly involves the math. So the most important thing about this law, and there's no special name for it. I like to call it the acceleration law. I sometimes call it the Fnet law. I sometimes also call it the math law. But the important thing about this law is it tells us that if we are in fact dealing in a situation where we have an unbalanced force, or in other words, a net force, then as a result, we are going to get acceleration. So Newton, in his book, actually described this law as that having acceleration or acceleration is a property that is proportional to our net force, so our unbalanced force, and inversely proportional to an object's mass. But of course, you guys are more familiar with seeing this as F net is equal to ma, because that's kind of how we showed you how to do it in Science 10. And in fact, that's the way I'm going to be using just to make things a little bit more convenient. But the most important part of this is the understanding that with an unbalanced force comes an acceleration. Okay, so let's have a look at this example and we can break down a little bit more about what this means or implies in terms of the other laws as well. So example number one says we have a 1,200 kilogram car accelerates from 10 kilometers per hour to 80 kilometers per hour in a distance of 200 meters. So the key word here, and the question asks us to list the forces that are acting against the car, and then we'll go from there. Okay, but the key word here is that we are dealing with an acceleration. So according to Newton's second law, it means that we have some kind of unbalanced force, okay, which essentially is code for telling us that we're dealing with some kind of net force. And I'll expand on this and say that this net force, I hope you can see it, is along our horizontal or along our x axes because we're traveling along a level road. So let's just say that our displacement is in this direction. And what we're going to be doing is we're going to be drawing what's called a free body diagram. So a free body diagram is a simple diagram that starts with a dot. So the dot here represents the object that I care about. So in this case, it's the car. And we're going to quickly summarize all of the forces that are acting on the car using this diagram. So the first force that we're going to have is we're going to have an applied force, right? That is pushing or accelerating the car forwards. And the question doesn't actually tell us whether or not there's friction, and it's not really going to matter in this case, but we'll say that there is. So we're going to say that we have friction going in the opposite direction of the applied force, and the friction obviously comes from the frictional force between the car's tires and the ground. Okay, so those I would say would be our forces along our x-axis. So we do actually have two other forces. Okay, we have gravity that is pulling the car downwards, and since the car is not actually accelerating downwards at all, we do actually in fact have a upwards force that's resisting this, I guess, pull downwards, and we call that the normal force. So normal force is a type of force that comes from a surface. So in this case, our car is sitting on a surface, and therefore we have a force that is pushing up against the car. Okay, so those are our four forces that are acting against the car. So part B allows us to do a little bit more of a deep dive on these forces. So the question says, what does Newton's first law tells us about the forces that are acting on the car? So if we are accelerating, and we are, right, because we're going from a smaller velocity to a larger one, so we're speeding up, it means that we have an acceleration in this direction. And according to Newton's first law, if we are accelerating, okay, it must mean that we have an unbalanced force along this axis, okay? And in fact, if we're accelerating to the right, okay, it's implying that this force is greater than this force, and then therefore we have a net force that is going in the same direction as the acceleration, okay? So what Newton's law tells us is that in the x-axis, okay, we have an unbalanced force, okay, and then this unbalanced force implies that we have acceleration. And I guess that's more about the second law, but whatever, we'll just put that in. The y-axis is also interesting because we can look at this as well. So I have a normal force and a gravitational force, and the car is traveling along a level surface. It's accelerating to the right, but it's not actually moving anywhere along our y-axis. So it's not going up, it's not going down, okay? And so relative to the y-axis, we can say that we actually have balanced forces in our y-axis. So the magnitude of Fn, whatever it is going to be equal in magnitude to Fg. They're just going to be opposite directions. So one's going to be positive, the other one is going to be negative. So in our y-axis, we have balanced forces. And balanced forces essentially means that we have no net force, we have no acceleration, and our car is going to be either moving in a constant velocity along our y-axis, or it's going to be stationary. In the context of this question, I know that we're stationary along our y-axis. All right. Okay, so having a look at part C, the question's asking us, what is actually applying the force causing the car to accelerate? So your gut reaction here is that, well, it's the engine of the car that's propelling the car forward. And that's not, obviously not incorrect. And I'll admit I would oftentimes kind of abbreviate and fall back to that. So that's useful to know. But what's actually happening is that the engine is causing the car's tires to rotate. And as the car's tires rotate, they actually push backwards against the ground. So we do actually have, if we want to be really, really, really kind of technical and specific, we have an action-reaction kind of relationship going on here. So the wheels are pushing backwards against the ground, and because of Newton's third law, it's actually the ground that's propelling or pushing the wheels, I guess, or the car forwards, right? So we have the wheels applying a force on the ground, and then the ground applying an equal and opposite force against the car, causing it to propel forward. So I don't know actually what we want to write for that. I don't know. We might just say the engine, but maybe you can say the ground pushes. So the ground pushes the car forward. And of course, you know that's because it's the wheels pushing backwards against the ground. Okay. And the final part of this question is what we're going to be looking at in terms of math. So the question asks now, what is the net force that is acting on the car? So this is a great question. So, and it is have to do with math. So maybe what we can do first is we're going to write down all the information that we know and then kind of go from there. So the question says that we're dealing with a car that has a mass of 1,200 kilograms. We have an initial velocity of 10.0 kilometers per hour, and we're accelerating to a final velocity of 80.0 kilometers per hour. Okay, and then it says during this time we're covering a distance of, I'm just going to have a look, 200 meters. Okay, and the question's asking us to solve for, not the acceleration yet. The question's asking us to solve for the net force acting on the car. Okay, so the first thing that we understand is that the relationship between net force and acceleration comes from Newton's second law. So our Fnet in this case is going to be equal to mass times acceleration. So, I mean, really, we're given mass and the car is accelerating, and we're given some variables here that we can actually solve for acceleration. So it's actually quite straightforward, right? So we're going to take our initial velocity, final velocity, and our distance and solve for acceleration. And then through that calculation, we can quite simply get our net force. But there is one thing I do want you to think about, and that is that this net force, although it is mass and acceleration, right? You do have to have an understanding that whatever magnitude this force, this net force is, it's going to be the difference between our applied force and our frictional force. And again, I'm not really sure if there's friction in this question or not. It doesn't matter. Okay, this is going to prove the point nonetheless. But this actually, in terms of forces, our net force here, it is the difference between these two forces. And then that difference is the same magnitude as mass times acceleration. So in this case, we don't need to worry about this and this because we're working with this relationship, but just kind of moving forward, that's something important for us to know. Okay, so it's a two-step problem. Our first step is going to be to solve for acceleration, and then we'll go back and use Newton's second law to figure out our net force. So I'm just going to draw a line here to keep organized. Okay, so I have VI, VF, D, and A. So it seems to me that the best approach here is going to be VF squared is equal to VI squared plus 2AD. So we do have to do a couple conversions here. So 10 kilometers per hour, we need to convert to meters per second. So I'll just do that real quick. So this is about 2.78 meters per second. And then 80 kilometers per hour, we'll have to do the same thing. So this is about 22.2 meters per second. And of course, when I use these numbers in my calculation, I'm not using the two rounded values that I wrote down. I actually have to go back and use that full calculator value, right? So let's go ahead and plug in our values and solve for acceleration. So we have 22.2 meters per second. Square that whole thing is equal to 2.78 meters per second squared plus 2 times the acceleration, which is what I'm looking for, multiplied by my distance, which is 200. And we're going to go ahead and solve for our acceleration. So I did not do the calculation yet, so I'm going to do this real quick. So I guess you don't have to pause here. You can just do this as I'm trying to do this. I hope I get it right. And I'm not going to double check. I'm pretty sure this is right. Okay, so I'm getting approximately, to proper significant digits, 1.22 meters per second squared. And it is worth noting that acceleration is a vector, so I do need a direction, even though my question didn't explicitly imply what is what. But this is, we'll just say it's in the positive direction. According to my diagram, it's towards the right. So what the heck? Let's just say towards the right. Okay, so that's great. You guys can work on the rest of the homework, and please let us know. So Google Chat is a great way to ask questions because we're all getting a little bit busy at home with taking care of our own kids. So sometimes we can't always meet, do the Google Meet thing, even though I will still try to do that. Email still obviously works as well. But Google Chat, I do have it on my phone. So if you ever have like a quick question, I may be able to get to it in a more timely manner. And then if I can't answer anything through like, I guess, written text, I can also send like a little screenshot of a worked out solution for whatever you need help with. So, okay, good luck.